Hi guys, today we're going to start talking about lesson 1.3, continuity. But before we can talk about continuity, we have to talk about this thing called a limit. A limit is the concept of approaching a value without necessarily ever reaching it. All right, so let's think about what that means. Take a look at this diagram here. You have a graph of a linear equation. And if you look right over here, we have a random value of x. We're going to call it c, right? So now what we want to do is we want to take a look at what happens to the y values of this curve as we approach c, right? So suppose I'm right here on the x-axis, right? And I'm moving towards that point C. Where is the graph? The graph is above me, right? But as I move closer and closer and closer, do you see how the graph inches its way further and further down? Now, as I approach C, what happens to the y value of the graph? It looks like it's approaching this vertical y value of L, okay? Now, what if I were here, okay? And I'm approaching C from the opposite side, from the right-hand side this time. Now, again, the graph is above me, but as I inch my way closer and closer to C, the graph is going further and further up. When I get really close to C and I look up at the graph, what vertical y value has it approached from that side? Oh, look, the same y value of L. That y value of L is called the limit. Okay, and because as our green man and the red man, as they were approaching C, the y value for both of them was approaching the same value L, we say the limit of this function as x approaches C is L. Let's say that one more time. The limit of this function, f of x, as x approaches C is L. Okay, did I ever talk about getting to that y value of L? No, all I ever said was it's approaching that value, okay? All right, so the way we define a limit then is if from the left and the right, as we approach a certain point, the y values are approaching the same y value of L, then the limit exists. Okay, let's take a look at some examples here. Look at this graph here, and we want to take a look at some of these limits. So first and foremost, I want to find the limit of f of x as x approaches -4. Okay, where is -4? Right here. All right, as you get closer and closer to -4 from the left-hand side, what y value is your graph approaching? It's approaching a y value of 3. Okay, we're not done evaluating a limit yet because we only looked at one side. Now let's take a look at the right-hand side. As I approach -4 from the right-hand side, and when I get really close to -4, what y value does the graph look like it's approaching? Y equals 3. Because from the left and the right, the graph was approaching the same y value, we say that is the limit of f of x as x approaches -4. Okay, let's take a look at another one. The limit of f of x as x approaches 1. Well, where is x equals 1? Here. Okay, As I approach 1 from the left, what y value is the graph approaching? -1. Okay. As I inch my way closer to 1 from the right, what y value is the graph approaching? -1. Is it approaching the same y value from the left and the right? Yes. So the limit as x approaches 1 is -1. Now, does the graph ever get to -1? No. Do we care for limits? No. It's only where the graph is approaching. That's what we care about. That's what a limit is. Remember what we said here? The limit is the concept of approaching a value without necessarily ever reaching it. Okay. What about when the graph, what about the limit as x approaches 5? Where the heck is 5? 5 is here. As I approach 5 from the left-hand side, okay, where is the graph approaching? What y value? Right over there. It's approaching +5. As I approach x equals 5 from the right-hand side, what y value is the graph approaching? Y equals 2. From the left, it's going up to 5. From the right, it's only going up to 2. Because the left and the right are not the same y value, we say the limit does not exist. DNE, okay, does not exist. I have to specify this here. It has to be DNE, not undefined, please. Okay? All right. Now, what about as x approaches 0? Let me remove some of the clutter here. As x approaches 0, as we approach 0 from the left-hand side, the y value is approaching 0. From the right-hand side, the y value is approaching 0. So this is 0. Okay. Now, that is limits. Notice we never spoke about the y values, actual y values, okay? Now let's talk about the actual y values. Let me erase some of this stuff. Let's talk about f of -4 here. F of -4. When x is -4, what is the actual y value? 3. Okay, that's the same as what we got for the limit. Cool. All right, what about at -1? What's f of -1? At -1, what's the y value? Nothing. It's a whole. It's undefined. Oh, that's different from the limit. That's cool too. What about at x equals 5? What's f of 5? Here, y equals 2. F of 5 is 2, right? No correlation. We got DNE for the limit. What about at 0? What's f of 0? 0. So I only do this to highlight the fact that the actual function values are meaningless when we talk about limits. They really are independent, and one is irrelevant when we're talking about the other. Okay. Now, let's move on to continuity. But to talk about continuity in math, we first talk about discontinuity. A discontinuity in a graph is a break in the graph. So we say a graph is continuous when you can trace it from beginning to end without ever having to remove your pencil from your paper. All right? So anytime then there is a gap where you have to remove your pencil, there is a discontinuity. Okay, there are 3 different types of discontinuities. The first one is like what you see here, there is a vertical asymptote. When there is a vertical asymptote, we say it's an infinite discontinuity. All right? That's the first case. When does that happen? It happens when you have a function, let's say like this, 2 over x minus 1, right? At x equals 1, there is a discontinuity, there is a vertical asymptote, and it's called an infinite discontinuity. Another type of discontinuity is a jump discontinuity. This happens for piecewise functions. Okay, this happens in piecewise functions, and it's literally where there is a jump in the y value. Okay. Next, this is perhaps my favorite, is a removable discontinuity. A removable discontinuity is a hole. When does that happen? So in the first example to the left, I said, when you had y equals 2 over x minus 1, the x minus 1, there is a discontinuity there. At x equals 1, you get a hole in the graph. But what if you have something like this? What if you have y equals, 3x times x plus 1 over x plus 1. Okay, so you factor this function and you get something like this. Clearly, at x equals -1, this function is undefined. However, look at what happens. You can actually cancel out that term with something from the top. You cancel it out and you're like, no, there was nothing there. Look, I removed it, right? Because it's something that can be removed, we call it a removable discontinuity. It only gives you a hole, not a vertical asymptote, right? Whereas in the case before, because that x minus 1 was there for good, it's there infinitely. You cannot get rid of it. It's an infinite discontinuity. Okay, now that we know all about the discontinuities, well, what is the requirement for a function to be continuous then? Well, just like with anything in math, we have a test, a continuity test. The continuity test has 3 parts, and it's an all or nothing deal. A function must pass all 3 parts or it fails. All right, first and foremost, f of x has to be defined at c. That means f of c has to exist, right? F of 5 is 7. Fine. Second, the limit has to exist. So you have to get like limit is equal to some number, 0, 1, -2, not d any. Third, that limit has to be equal to f of c. So like you see how here, right, there is a limit of 3. F of -4 is 3. When those two values are the same, that's when the function is continuous, right? Here too, when those two values are the same, that's when the function is continuous. Okay, so let's take an example here. Determine whether this function is continuous at the given x values. Justify using the continuity test. Okay, and then if it's not continuous, we have to specify what type. The function we're given is x squared plus x plus 1, and we're looking at x equals 1, right? So I don't care what happens at x equals -3 or 7. It's just at x equals 1. This is a very calculus-y thing where we only look at a function at one specific point. Okay, so step 1, you have to find f of 1. Well, f of 1 is 1 squared plus 1 plus 1, 3. Next, we want to graph f of x on a calculator and basically look at its limit. So let's go ahead and do that. Right, so here's my graph, and all you have to do here is nothing fancy, just visually inspect what is the limit as x approaches 1. One way to do that is if you trace, right, at x equals 1, right, find the point at x equals 1. Okay, so look at that. Immediately before it, what's the y value? About 3. Immediately after it, what's the y value? About 3. That tells you that the limit of f of x as x approaches 1 is 3. Now, here's what cinches the deal, right? Are the results in 1 and 2 the same? Well, you have to justify, you have to say the step. You say f of 1 is equal to the limit of f of x as x approaches 1. Therefore, right, that's not hieroglyphics, that's, you know, the 3 dots in math means therefore, f of x is continuous at x equals 1. All this straight out of calculus, right? So I want you guys to get used to this notation. Okay, so let's take a look at these, right? We're just going to go through them. Okay, so first of all, we're going to do part 1. F of x is this at x equals 2. Well, f of 2 is 2 plus 1 over 2 minus 2. 3 over 0, undefined. Okay, it already failed the first condition, right? F of c does not exist. So you say, therefore, f of x is not continuous at x equals 2. By the way, this function is perfectly continuous at all other points, right? It's just at x equals 2. So you have to specify that. Now, what kind of discontinuity is it? Well, let's inspect this function. This is a rational function. At the denominator, right, at x equals 2, you get 0. Can you cancel that term in the denominator with anything from the top? No, that thing is there to stay. So this is an infinite discontinuity. Okay, what about this one? F of negative 3. Again, we get negative 3 squared minus 9, negative 3 plus 3. This is undefined, so again, it fails. Okay. Now, so f of x is not continuous. Now let's see what kind of discontinuity it is. In this case, let's factor out the numerator. Okay, so clearly at x equals negative 3, the denominator is 0, so it's what do you call it? A discontinuity. Okay, but look, you can cancel that with something in the numerator. And since you can cancel it, you say it's a removable discontinuity at x equals negative 3. Okay? All right. End behavior. End behavior, you did it last year, right? It's what happens at the ends of a graph, right? And when we talk about end behavior, we talk about it from the right and from the left. Right end behavior is what happens to the y values of the graph as x approaches infinity. So as you go to the right end of the universe, where does your graph go vertically, right? In this case, it goes down to negative infinity. Now in algebra, you used some different notation. You said as x approaches infinity, blah, blah, blah. Well, here we're going to condense it. we're going to say the limit of f of x as x approaches infinity is negative infinity because it's going down. Well, what about the left end behavior? Well, as x approaches negative infinity, as you go to the other side of the universe, what's happening to your y values? Oh, they're going up. So we say the limit of f of x as x approaches negative infinity is positive infinity. Okay. All right, so let's take some examples and let's do some some end behavior. Okay, when you see the words end behavior, you have to look at the far right and the far left. So we say limit as f of x, limit of f of x as x approaches infinity, limit of f of x as x approaches negative infinity. Right. As I move to the far right, what's happening to the y values of this graph? Oh, it's leveling off at y equals 0. So the end behavior is 0. Well, what if I move to the other side? What's happening to the y values? Oh, they're leveling off at 0. So the limit as f of x approaches negative infinity is 0. Okay, what about here? Limit of f of x as x approaches positive infinity. Well, as you go to the far right, where's your graph going? It's going up to positive infinity. Limit of f of x as x approaches negative infinity. As you go to the far left, the graph is going down, so it's negative infinity. Okay, so take a look at this one. We're going to use our calculators here to graph each function and then identify and describe points of discontinuity and so on. Okay, so in the first case, what is the discontinuity and type? Well, you should be able to, take a look at this and say, okay, it's a polynomial function, so there are no discontinuities. Okay. All right, so let's take a look at right and left end behavior when we graph. Okay, so when you take a look at the graph, you see that as you move to the far right, the graph is moving up, so the limit is positive infinity. And as you move to the far left, the graph is going down, so it's negative infinity. Zeros. You can either, do the zero function, menu, analyze graph, and so on. But we can already tell that this is crossing the x-axis at -2 and 1 and 2. So the way we write it is, you say f of -2 is 0, f of 1 is 0, f of 2 is 0. Okay? All right. For the next one, I actually have it here. When I graph, that's what it looks like. Okay, so first of all, discontinuity. Okay, there is a major discontinuity, it looks like, at x equals 0, right? So I say infinite discontinuity at x equals 0. Okay, limits. As you go to the far right, it's leveling off at 0. So the limit is 0. Far left, it's also leveling off at 0. And then next, what you want to do is you want to find the zeros of this function. So we're going to do analyze graph this time. 0, the first one is here. 1.19. So I'm going to do f of 1.19 is equal to 0. And then the other one is at negative 4.19. Okay? All right. So, okay. So here, determine the value of a so that f is continuous. Now, for a function to be continuous, there can't be any breaks, right? So at a specific point, the left and the right have to have the same y values. All right, so take a look at what, this looks like here. It looks like this is a piecewise function with a partition at x equals 2, right? And then what does this look like? At x equals 2, this function has a y value of 5 here. And it looks like this is actually a parabola, right? So when I graph it, you don't really have to do this. I'm only doing it to show you guys what happens here. That's the function to the left, okay? Now, in order for this to be continuous, the function to the right has to pick up where that one left off. That means at that point, at x equals 2, the left and the right have to have the same value, right? Should have same value. All right, so what's the function to the left? At x equals 2, the function to the left is x squared plus 1, which is 2 squared plus 1, which is 5. Okay, on the right, at x equals 2, the function is ax, which is a times 2, 2a. So now, to be continuous, the left and the right have to be equal to each other. So you say 5 equals 2a and solve for a. So at a equals 5 over 2, this function is continuous. Right. Last but not least, a car rental company charges a base fee of $35 to rent a car with a daily fee of $15. Write an equation that models the total rental fee as a function of the number of days n. Okay, function of the number of days n. That means I need a function notation. And if it's a function of the number of days n, it has to be f of n. That's the point of this problem. I know you guys can write the function, but the point of this problem is that you are able to call it f of n. So the rental fee, it's $35 plus $15 per day. B, as the number of days increase, what value does the cost approach, right? This is an end behavior problem. So when it says increase, assume it increases infinitely. Okay, so this is an end behavior problem. So we say the limit of f of n as n approaches infinity is the limit. What is the limit? So look at this function here. As n approaches infinitely, how much money are you going to pay them? Well, infinity. Okay? All right, guys, thank you so much. I will see you in class.